Okay, hi everyone. So we have an additional method for solving a system of linear equations in which we can utilize this LU factorization. So the reason behind LU factorization is that we can factorize this matrix A to be able to solve this linear equation, which is the AX is equal to B. So decomposing this into L and U, we can solve this X here. So why is that? No? So it seems troublesome to solve for L and U just to solve for X. No? Why do we have to factor this this matrix A? So usually LU factorization is mostly practical for problems wherein the coefficient matrix A is constant and the only changing variable is B. So for repeated computation, it is practical to use LU factorization in comparison to Gaussian elimination and Gaussian elimination. Again, if your A matrix is constant, non-changing, and your B will be changing for your processes, then LU factorization will be practical. So again, LU factorization, we are factoring here. So given this matrix A, it could be factored into the L and U. Okay? So we have different known methods. We have the Krauts method, the Doolittle's method, and the Cholesky's method. But for this course, I will only discuss this Doolittle's method. Okay. Okay, so for the Krauts method, what happens in the Krauts method is that it still has an L and U matrix. But as you can see here in the Krauts method, the one diagonal is in the U matrix. For the Doolittle's method, we still have the L and U, yes, but the one here is in the L matrix. Okay. For the Cholesky's method, this is only applicable for symmetric matrices, or to be specific, a positive semi-definite symmetric matrix. No? Okay. So we can do this for this symmetric matrices only. And we can do this for either we transpose this L or transpose this U times U. So the steps involved in solving system of linear equations using LU factorization will be this diagram. So we have this given matrix A, we have the unknown X, we have the constant P. So the first thing that we should do is to factorize this A into L and U. And then after that, we have factored this L and U. We will now substitute this L to this LD is equal to B to solve for D. After solving for D, we can now use the U and the D to solve for X. Okay, so the process here will be, this is the factorization process. We will utilize the forward substitution and also the back substitution. Okay, so let's have an example of finding the solution of this using LU decomposition method. So how do we do this, LU decompositions? I will just show you the technique. Okay, so the first thing we should do is to find the U matrix. So to find the U matrix, we just want to find the, in some sense, the row echelon form of this matrix. So we are only focusing on this matrix A, and then we want to make this three entries here into zeros. So this will become what, no? So let me just copy the first row here. For the second row and third row, we want to use the operator. So for the second row, we have R2 is equal to R2 minus, so this will be 0.1 over 3. And then we have R1. For row 3, we have row 3 minus 0.3 over 3. And then R1. Okay. Let's just make this closer. So using our calculators, we have, what are the values here? So for the second row, alpha A minus 0.1 over 3. alpha t. So calc and substitute this 0.1 and 3. So this will be 0. Now just to confirm that this will become 0. And then, what's the next one? 7 and negative 0.1. So 7 and negative 0.1. So we have 7.0033. Okay, and then we have negative 0.3 and negative 0.2. So 0.0067. Okay. And then for the next row, we have a different formula. So let me just change this. Okay, and then substitute the values 0.3 and 3. I'm just to try if this will become 0. Okay, it became 0. It has became 0. So negative 0.2 and negative 0.1. Negative 0.1. So negative 0.19. And then 10 and negative 0.2. So this is 10.02. Okay. 0.12 pala. Right? 0.2 or 0.12. I think we did something wrong here. Let me just check this. Ano? Let me just check this. So negative 0.3 and we put a different. Okay, so we have error here. 0.2933. Or sorry, negative. And for the last entry, I think we did something wrong here again. So 10 and negative 0.2. Oh, is it negative? Is that right? I'm confused. 0.02. So 10 and negative 0.2. Okay. Okay, we have to change this again nga pala. Okay, so the last one, so we already changed this into zeros. We will now change this into zero. So for the last operation, we have R3. We have R3 minus we have negative 0.19 over 7.0033 or 2. Okay, so this will become positive now. Okay, so substitute the values again. We have 7.0. Yeah, okay. So calc and negative 0.19 and 7.003. Huh? I think we did something wrong again. So calc where did we go wrong? What? So calc is okay, that is right. 7.0033. Huh? Stop it. Ah, 0, 0. Okay, I found it. Okay, so this will be 0. So 0 and 0. And then for the last one, we have calc and 10.02. And negative 0.29. This will be 10.0120. So copy the remaining rows that we did not operate on. 7.0. Okay, so this will be now your row echelon form of this matrix. And this is actually already your U, no? In the Doolittle's decomposition. So this will be your U matrix here. How do we now define the L matrix? So for the L matrix, if this is a 3 by 3, then your L matrix will also be a 3 by 3. With, no, as you can remember, the Doolittle has 1 as its diagonal and zeros in their uh, upper triangle, no? So what should be the entry here? So the entry here are the values of the alpha that we utilize. Or to be specific, the negative value of this alpha. So if this is your alpha, then the negative of this will be, so negative of negative 0.1 over 3. So basically, we'll just change the signs. So this will be 0.0333. All right. And then for the other one, we have positive as well. No? This will become positive. So 0.1. And then for this one, so then since this is positive, this will now become negative. So we have negative 0.19 over 7.003. Okay, so we have negative 0.0271. Okay, and then 1 here. So this is now your L matrix, and this is your U matrix. So what's next? So the next thing is, if you can remember, we want to utilize this this L and B to solve for D. So we have LD is equal to B. So to solve this, we will utilize back substitution or forward substitution. So we will utilize forward substitution. So basically, your L matrix here will be, we have 3. We have 3 here, and then negative 0. Sorry, or L nga pala ay this one. Oh. We have 1, 0, 0, 0.333, 1, 0, 0.1000. This is too small pala to write on. 1, 0, sorry, 0, 1, 0, 0, and 1. And then D here will be, let's say, this D1, D2, and D3. And then equals to B. So B here is your constant matrix, or constant row vector, 7.8. Negative 19.3 and 71.4. Okay, so forward substitution, we already have a solution for D1. So we have D1 that is equal to, we have 7.8, as you can see. So D1 is equal to 7.8. So we have D1 or 0.333 D1. We have just write here D1, D2, and D3. So we have D1 or 0.333 D1 plus D2 is equal to negative 19.3. So we can just write this down as 0.333 and then 7.8. 7.8. And then we have plus D2 is equal to negative 19.3. So what is D2 here? So D2, we can just transpose this back and forth. So D2 will be 0.333 times 7.8 plus 19.3. Is it 7.85? Why is it 7.81? Right? Why is that? 21.57. I think I will have okay, I think I have another problem here. Oh, sorry, negative pala to, So negative. Oh, we did this wrong again. To transpose this one to the other side, we have negative 19 minus 0.333 times 7.2. Okay, negative 21.8974. I think I have something wrong here. Just check. Why is that? Why do I have it wrong? This one. Why is that? Is there something wrong? I'm skeptical about my answer because it is different than my notes. Oh. Okay, let's check my oh 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 oh. This should be 7.85. It might be even. Okay, sorry. This should be 7.85. I'll just change this. So this should be different. So this would be 7.85. This will also be 7.85. Okay, and then D2. Let's check this. 0.0333 pala to, no? So we have another error here. Okay, I found it already. So be careful with when solving using your calculator. So yeah, so we found the answer. So negative 19.5614. Sorry for that. So we have this as our D2 and then D1. So for D3, okay, I guess I can fit this here. So we have 0.100 and then 7.85. And then plus, or sorry, minus 0.0271. We have negative 19.5614 plus D3 is equal to 71.4. So I'll just write this here. So D3, that will be equal to, so you have 71.4 minus 0.1 times 7.85. This will now be positive and then negative. So minus 0.0271 times 19.5614. So 70.08. Is that correct? Okay, that's correct. 0849. 70 point, yes, 70.0849. Okay, so the next portion, finally, so D, that will be equal to, so we have, this 70, sorry, D1 is equal to 7.85, D2 is is negative 19.5614. And then D3 is 70.084. Okay, so the next step here will be using the UX. Okay, sorry, UD is equal to X. UX is equal to D pala, no? Sorry. Okay, so we have the matrix U as this. So we will write this down again. This is a very long solution. I feel bored. So negative 0.1 and negative 0.2. 7.033, negative 0.2933, 0, and 10.012. So the x here will be the x1, x2, and x3, and then equal to d. So d here will be 7.85, negative 19, and 70.0849. Okay, so for this last step, we will now perform back substitution. So we will start from the very last row and then upwards. So we're already familiar with this. So x3 is equal to 70.0849 over 10.12. Okay, and then for x2, I'll just write down every solution now for now, no? So for x2, so we can substitute the value of x3 here. So this will be negative 19.5614. And then transpose, so sorry, not this one, the other one to the other side. So this will be negative 7.0. I think this one pala, no? This is correct. So sorry, this will become positive 0.2933 multiplied by x3 and then divided by 7.0333. Okay, and then for x sub 1, that will be equal to, so transpose this, so we have 7.85 minus, or sorry, this will become positive 0.1, so x2, and then plus 0.2, and then x3, and then all over we have 3. Okay, let's do this combination. We have 70.0849 over 10.12, and then 6. This is the answer. Why is it? I think it is wrong. Let me just check again. Where's my... What? Why? 012. Okay. We have another error. Ano, ayan. 7.0001. 7.0001. And then 7.0001. So substitute the value here. So negative 19.5614 plus 0.2933 times 7.0001. 7.0333. So we have negative 2.48. Where did we go wrong again? We got it wrong again. No. Okay, I think it's the answer, no? Negative negative 2.4893. Okay, and then for this third one, we have substitute this first pala, no? So this will be negative 2.4893 and then 7.0001. So x1, that will be equal to 7.85 plus 0.1 times negative 2.4893. plus 0.2 times 7.000. Okay, so this will be 3.004. This will be your answers. So using LU factorization, this will be your answer. Therefore, we can also write this as 3.0004 and negative 2.4893 and 7.0001. So this is your basically your x1, x2, and x3. Okay, so that will be all for this problem. Let's see the comparative efficiency of the three different the different the three different methods, so direct methods. So comparing the number of equations, as you can see now, versus the relative computational effort of the three direct methods here. So the LU decomposition, Gaussian elimination, and the Gaussian elimination. As you can see, the most efficient still will be the Cholesky. No? Assuming that it is a symmetric matrix, of course, this will be the best way to go. But usually, matrices aren't symmetric, no, in nature. So the best bet to use is still Gaussian elimination, but you can also still use Gaussian elimination. So the higher the number of equations, as you can see, it to base some what do you call this? It flattens out, no? The computational effort flattens out as we increase the number of equations. Okay, so that will be all for the computation efficiencies, and I guess I'll just add this few notes to finish off. No, so round of error as well as time required to solve the equations depends on the total number of arithmetic operations performed. The time required to perform the multiplication and division operation is approximately the same. Time required to perform addition subtraction is considerably small compared to multiplication or division. So what does this mean? No? So we have the round of error as our potential issue with direct methods, and the time required for multiplication and division and addition and subtraction will be the two things that will affect this computational effort. So round of errors, precision, and precision wise, and the time needed. We could optimize for time, no? Rather than yung round of errors. And then for larger equations or larger system of equations, it might not be accurate since the rounding error will be much more apparent. So there is no, what do you call this? There is no self-correction property when using direct methods. So we will see this later now when comparing Gaussian elimination with, let's say, Gauss-Seidel in the iterative methods. Okay, so we should use Gaussian elimination for the for a number of equations less than 50, but for larger, we can utilize the iterative methods. So this is the theoretical, no, we can say that the rough approximation limit of number of equations before we can utilize the iterative methods effectively. Okay, so that will be all. Thank you guys.